There are a number of items that we need to go through, except that I'm going to kind of go through them quite fast. The first one is the concept of adjacency. We know that two basic solutions are adjacent if they share how many? n-1 linearly independent hyperplanes. So this is the definition that I gave you before. Two basic solutions are adjacent if they happen to share n-1 of the linearly independent active constraints. For a standard form, where you've got the constraints in ax equals b and x greater than or equal to 0 form, we have, of course, adjacency if this amounts to having now in standard form what we have is you've got two solutions under consideration. Okay? One of them has n linearly independent, plus possibly more. Okay? But you've got n linearly independent active constraints at 1. For the other one, you've got, again, the active set, again, n. And if they share n-1 of them, then adjacency occurs. Which means that since the active constraints are defined by ax equals b, and you pick n-m active constraints from the non-negativity part, this amounts to having n-m-1 common active constraints from the x greater than or equal to 0 part, okay? Because both will satisfy ax equals b at the same time, okay? So the only freedom you have is for the other one. So that's why you reduce that by 1 to have n-1. Or equivalently, m-1 of the variables that are solved for. These are the variables that are not set equal to 0. You are solving for them, are common to both solutions. Okay, we'll come back to these things perhaps at this in the discussion of the simplex method. I could give you an example, but let's just omit the example. Let me just give you one additional issue here that we sort of discarded. That's the issue when A does not have full row rank. These are sort of issues that you need to know about, except that I'm not going to go through the proofs. So we assume we have a matrix A, which is m by n. And so let me just state the theorem here. I think it's supposed to be number 5, I guess. So let P be the polyhedral set defined by ax equals b and x greater than or equal to 0. That's the standard form polyhedron. And let's just assume P is not empty. A is m by n. And rank of A is, say, k, which I assume is less than m. So it does not have full row rank. And you've got, since the rank is k, you have a choice of row indices, which I call I sub 1, I sub 2, etc., I sub k. Okay, you have k such rows. These are rows because of the superscript notation I'm using. And that, let's just put the word, and that the rows ai1 through aik are linearly independent. Of course, the existence of such rows is guaranteed because the rank is k. Okay? All right, so under these conditions, if I define a new polyhedron, Q, consisting of the set of points xRn, where non-negativity is still preserved, except that the equality part is replaced by A prime and B prime, where A prime is the k by n submatrix of A, consisting of rows ai1 through aik. So you take these linearly independent rows and put them in a matrix. You discard the remaining rows of A, you just throw them away. And B is defined similarly. B prime is defined similarly. It consists of the right-hand sides corresponding to these indices. Okay? So the claim is Q is the same polyhedral set as P. Proof omitted. Work on it at home, if you wish. All right, the significance of this is we developed theory for the, or under the assumption that A has full row rank. All the theory rests on that assumption. And if that is not the case, of course, then you should not have a special case. In other words, whenever that condition is not satisfied, you should be able to convert the polyhedron into a form that satisfies the condition. So A prime, in this case, will have full row rank. It will be K. Okay? So everything that applies, all the theorems that we use will apply to this rather than that. But Q and P are the same, so there's no problem. Okay? All right. Let me also give you a few words about degeneracy. Again, these are deeper concepts, except that we're sort of passing through them quickly. Okay. A basic solution in Rn is degenerate if there are more than n minus more than n active constraints at that point. Of course, we're defining it relative to a polyhedral set. Okay? Just a quick example. If you've got, for example, we're in 2 dimensions in this example. This point, all of these lines are defining hyperplanes, or this is the feasible set, or the polyhedral set. This one is a basic solution which is degenerate. Degenerate basic solution, or degenerate extreme point. Since basic solutions, well, we're defining basic solutions here, so it's a degenerate basic solution. This particular one here is a degenerate basic feasible solution. It's part of the feasible set, or it's in the polyhedron. And this point here is a non-degenerate basic feasible solution. Why are these degenerate? Because you've got more than 2 intersecting. Okay? Now, this is, of course, for the general polyhedral sets. For standard form problem, for standard form polyhedrons, this amounts to having more than n minus m active constraints taken from the non-negativity part. Okay? Of course, those active constraints coming from the non-negativity part are the non-basic variables, if you remember the word. I never really use the word non-basic here, but nevertheless, that's what it amounts to. Okay? All right. Existence. Does all non-empty polyhedron have an extreme point? The answer is no, not necessarily. Okay? Some polyhedral sets do not have extreme points, in which case, of course, things may not be very pleasant for you. Remember that if you're in n-dimensional space, Emre, can we open a window? Okay. If you're in the n-dimensional space, and if you have less than n constraints, in that case, regardless of how many of them are active, you're not going to be able to generate an extreme point. Okay? That's, of course, one possibility. Number 2, if you look at an example where you are in 2 dimensions and there's only one constraint, it's this one. There's only one. The other ones, even though I put them as axes, but they are not constraints, so maybe we should remove them. Okay? Let me just remove them. You're in 2 dimensions, and there's only one constraint like this. In this case, of course, this has no extreme points. Or if you're in 3 dimensions, and if you have some kind of a hyperplane extending in all directions, or possibly this hyperplane extending in these 2 directions, and another hyperplane intersecting it, like this. So the feasible region is this one. Can you sort of envision what's going on? You've got two hyperplanes intersecting, but the intersection is this entire line. There's no extreme point here. Okay? All right, so how do we characterize the existence or non-existence of extreme points? Well, this is the way we do it. By the existence or non-existence of a line. We say a polyhedral set P has a line if, or contains a line if there's a point X in P, and, of course, so by assumption, to have a line, you must have a non-empty polyhedron. There's a point X in P and a non-zero direction vector D such that the points formed by taking X plus lambda D is in such points will be in the polyhedron for all choices of lambda. Positive, negative, 0, everything. Okay? So in that case, of course, here's your point X in the polyhedral, for example. And you have a direction D. Suppose D is pointing this way at the origin. So when you take X plus, this is the point X plus lambda D. Okay, this is the point X plus lambda D when D is pointing this way. D is pointing that way. Okay? So when you increase lambda in the positive portion of the real line, you're generating all these points starting from X and going all this way. That's called a half line. If you take negative lambdas, you start generating all these points. That's another half line going the wrong or the other direction. Okay? So the union of these two half lines is your line. Okay? So here's the theorem. Number 6. Let the polyhedral set P be defined by AX greater than or equal to B without loss of generality, with A being m by n. And assume that P is non-empty. Then the following statements are equivalent. If and only if A, so A is true if and only if B is true, if and only if C is true. A says P has an extreme point. B says P does not contain a line. And C, there are n rows of A that are linearly independent. So, in order for a polyhedral set to have an extreme point, it should not contain a line, which is equivalent to having n rows of A that are linearly independent. You may have more than one such set of rows. Okay? Proof omitted. It's a long proof, believe me. But improving this if you prove these implications, then you will be done. But some of these proofs require subspace arguments, so you should be careful with these things. Okay? Or watch my old video. I think I have a proof there for this. Okay? So what are the consequences of this? First of all, if P is bounded, well, a bounded polyhedral set, of course, does not contain a line, so it must have an extreme point. Bounded means you can contain the polyhedral set in a sphere of finite radius. Okay? So, whenever a polyhedral set is bounded, it cannot contain a line. What about the set consisting of non-negative vectors? This set does not have an extreme point because it contains a line. Or does it? Which way? Does it or does it not? Of course, it doesn't. Or does it? Huh? It does not. Does not contain a line. So it must have extreme points. Okay? What is the extreme point we're talking about? The origin. Yes, the origin is the extreme point. Because this does not contain a line. In 2 dimensions, of course, you can see that it cannot contain a line because you're in the non-negative orthant. The same, of course, is true for higher dimensional sets. For this reason, the standard form polyhedron always contains an extreme point. It always has an extreme point. Why? Because the standard form polyhedron has AX equals B and the non-negativity. Since the non-negativity already tells you that you cannot have a line, of course, then the intersection of AX equals B with the non-negative orthant will not have a line, okay? Which means you have an extreme point. So for standard form problems, the existence of extreme points is always guaranteed. And with that, we can prove that whenever there's an optimal solution to a linear program defined on a polyhedral set, there's an optimal extreme point solution if the polyhedron contains an extreme point. Okay? Consider the linear program, minimize C trans, Cx, C is already a row vector, X in some polyhedral set P, where P is a polyhedron. If this linear program has an optimal solution if P has an extreme point, then there exists an optimal solution which is also an extreme point. And there exists an optimal solution which is an extreme point. Of course, this has one important consequence. Whenever your linear program has an optimal solution, you need not go through an infinite search in the feasible set. You can only focus on extreme point solutions, which are definitely finitely many. So that, of course, takes you from an infinite search to a finite search, even though the finite search requires usually many extreme point evaluations. Nevertheless, at least it's finite. You know, that's much better than infinite. Okay? All right. Proof, well, this has a short proof, but I'm going to omit it. It's really nothing difficult. It's not trivial. I mean, you know, you need to give good arguments, but it's compact, you know, you can do it. Okay? So, here are some consequences. If the polyhedral set on which the linear program is defined is empty, then the LP under consideration, this one, is infeasible. So whenever it's infeasible, of course, you don't have an optimal solution. Okay? If P is non-empty, and if there exists a point x bar in P such that the cost obtained by x bar is less than or equal to the cost obtained by any other x for x in the feasible set. Okay? So if these two conditions hold, then of course there's a finite optimum solution. X bar is one such optimum. So then the optimal cost, what is the optimal cost? It's this value. The value you get from the dot product of C with x bar, okay? That number, the optimal cost, is finite. And is equal to, you get whatever you get from an optimal solution. Of course, every optimal solution gives you the same finite optimal cost. Okay? They all share the same cost. But, so, the value, the optimal cost is unique, but there may be many different optimum solutions. Okay? Last condition, or the last possibility, if P is non-empty and there's no optimal point, then for every feasible solution x, we can find a feasible solution x prime such that Cx prime, the value you get from x prime, is better than or smaller than the value you get from x. This is doable for every x, for every feasible point. So, this condition cannot be fulfilled. Okay? That's what it means to be unbounded, or in that case, the optimal cost can be made arbitrarily small for a minimization problem. Well, it's not the optimal cost, but the cost, the objective value, can be made arbitrarily small. So we say that the optimal cost, even though it doesn't exist, is minus infinity. That's just a convention, just by convention. Okay? I'm going to take this down. Does everybody have it? You have it? It's gone now. Okay. A few more geometrical concepts until we get to the bottom of this. One is the concept of a ray. Given a point x in n dimension and a non-zero vector d in Rn, the set of points of the form x plus lambda d for lambda non-negative is called a ray with tip at x, or with vertex at x. So, if x is here, then this is the kind of thing where d points this way. So any non-negative multiple added to x will generate a half line like that. Okay? Half line or ray. Okay. Let's also talk about directions of convex sets. For a convex set S need not be polyhedral here. Okay? For a convex set S, a non-zero vector D in Rn, of course, for a convex set S in Rn, a non-zero vector D in Rn is a direction some people refer to it as a recession direction. Okay? It's called a direction of S if the ray x plus lambda d originating at X is in S. So every point of the form X plus lambda D is also in S. So for example, if your set looks something like this, that's your S. If you pick a point here, and if you pick this direction, then you start generating all this ray here. And of course, any point on this ray is inside your S. Okay? All right, so in this case, D is certainly a direction of the set. So let's look at the special case of polyhedral sets. Suppose you have a polyhedral set defined by the set of points, say, X in Rn, where you've got, say, a matrix A1 times X is less than or equal to, say, a vector B1, and then another matrix A2 times X greater than or equal to B2. These are all vectors of conformable dimensions, okay? And you've got also A3X equals B3 for some A3 and B3. At least one of A1, A2, or A3 is non-vacuous, but some of these matrices could be vacuous, or they may not be, there, okay? All right, so in this case, the set of directions of P can be identified through the use of these matrices. All you have to do is you just replace the vectors B1, B2, and B3 by the zero vector of the same size. Okay? So the set of directions of P is the set consisting of D such that A1 D is less than or equal to 0, A2 D is greater than or equal to 0, and A3 D is equal to 0. Why is that true? So it's really easy to find it. Rather than giving you a formal proof here, let's just give some arguments to make sure that you understand what's going on here. So let's consider, for example, the case A3X equals B3. Okay? Now, if you have, let me call this set D. Let's give a name to it. Okay? If D is a direction of the set, so if D is in capital D, then of course X plus lambda D is in P for all lambda greater than or equal 0. Okay? Then what do we know about this? Then of course A3 times X plus lambda D must be satisfied, which means that this should hold. What is B3? This should hold for every lambda non-negative. But when you multiply this out, you get A3x plus lambda times A3d. But A3x is already equal to B3 because x is in the feasible set, or s is in the polyhedral set, which means that you've got B3 and B3, so they cancel. So you have to have, so from here, you have to have lambda times A3 times d is equal to 0. Of course, lambda is a constant here. If it's 0, nothing happens. I mean, both sides are satisfied. But this should be satisfied for non-zero lambda. So that means, of course, A3d must be equal to 0. So d is orthogonal to every row of A3. Okay? You have to have that. Otherwise, it won't be a direction. You can prove the converse of this. Whenever this is satisfied, then, of course, D will qualify, at least for the equality portion, to be in D. But you must also check the other parts. Okay? Similarly, if you consider A1x less than or equal to B1, this part, if D is in D, then we must have that A1 x plus lambda D being less than or equal to B1 for every non-negative lambda. And this part gives A1x plus lambda times A1d less than or equal to B1. So what do we know about this? This is already less than or equal to B1. Okay? And this should be true for every lambda. But then what is the situation? If this is less than or equal to B1 and this is B1, if this part without the lambda, A1 times D, is not less than or equal to 0, so if A1D is not less than or equal to 0, what does that mean? That means there's at least one component of the vector A1D, A1 times D is a vector, okay? There's at least one component of that vector which is greater than 0. But in that case, there's a row of A1, say the ith one, whatever, okay? And we know that this is positive, okay, in this case, if this is not the situation. And in that case, of course, AIX plus lambda times AID. Now, this part is less than or equal to some number, say B1I, the ith component of the vector B1, okay? And this part is positive, and you require this to be less than or equal to B1I, the ith component of B1. Can you achieve that for every lambda? You cannot. Since this is positive, even though this part is strictly, or if equality, of course, it's, as soon as lambda becomes positive, you have a violation of the inequality. If AIX is strictly less than BI1, you've got some freedom, but when lambda is made large enough, of course, you lose that freedom, and the inequality turns the other way around. Okay? All right. So, can't have this if D is a direction. Okay? Similar argument goes for the remaining case, A2x greater than or equal to B1. So, this is correct. Okay? Of course, this is only the proof of one way. Which way is that? Whenever you have a direction, it must be the case that these are satisfied. But then you must also prove that whenever these are satisfied, it must be a direction. Okay? So don't forget that. Do we have some time? Maybe a few minutes? How much time do we have? Huh? 2 minutes? Yeah. Let's do an example, just a quick one. So I've got 4 inequalities in 2-dimensional space, and it gives me the polyhedral set. Of course, when you plot this, you get something like the following. You have one constraint that goes like that. That's your number 2 constraint. And this is 0, 2 here, this point. Number 3 constraint tells you to go that way. Number 4 tells you to go up. And number 1 is this one. And the intersection here is the point 2, 4. Okay? So your P is here. Now, to form the set of directions of this, all you do is you replace the inequalities with the right-hand side being 0. So these define you the set D. Let's call them 1 prime, 2 prime, 3 prime, 4 prime. Okay? So again, if you plot them in the 2-dimensional space, you have 3 prime, which is this one. That's your 3 prime. Number 4 prime is this one. 2 prime is obtained by moving number 2 parallel to itself until it passes through the origin. So it will look something like this. And 1 prime, again, you move it until it passes through the origin, because that's incorrect. That's 0. Nobody points that out to me. That's 0, right? Yeah. Okay. And so that one goes something like this. That's your 1 prime. You can see that obviously this has quite a bit of relationship to this one. You can see directly from here that the set of directions are these ones. You know, all those in between, where this one is pointing that way, okay? And this one is pointing this way. That's formally defined here. It's the same thing. Okay? So you've got the idea here. Let's stop here.